So we were discussing three different types of variabilities that can affect a manufacturing process. We talk about the natural variability. We talk about the preemptive variability, or the variability that is caused by preemptive outage. And then we started discussing the non-preemptive outage, but we didn't complete the discussion. So we're going to start from here today. And so we first need to define what is a non-preemptive outage. And these are the ones that represent downtimes that will inevitably occur, for which we have some control as to exactly when are they going to happen. Okay, so we can control this, and some of the examples that I mentioned last time is when the tools start to become dull, and you know that at some point you might need to replace it. You can decide whether you want to wait or when you want to perform that maintenance right away. So you have some control over that decision. Process changeover setup can be regarded as non-preemptive outage when they occur due to changes in the production as opposed to changes in the product. Okay, and as we saw for the natural variability and the preemptive outage variability, we have some expressions that we can use to account for that in our process. So the analysis for this case would involve an average number of jobs between setups, because now we are going to be controlling the number of jobs that we're going to wait until we're going to perform the next setup for our process. We also have an average setup duration, so how long this is going to last, and we also have some type of standard deviation to account for the variability of that duration. And as we did for the other analysis, we compute the coefficient of variation. We also compute the capacity effect, and we can put those things together to come up with an expression to account for the variability of those non-preemptive effects. So the variability effects, the setup, also inflate the process time capacity variation. Okay, so we're going to use this new set of equations to analyze how can these affect our processes. And I think in terms of observations, the setup increase mean and variance of processing times. The variability reduction is one of the benefits of flexible machines. However, this interaction is very complex to understand. So the next thing we're going to do is to see how can we observe these effects by using an example. Okay, so we're going to start with a fast, inflexible machine, which requires 2-hour setups every 10 jobs. Okay, and for that, we're going to have a T0 equal to 1 hour. We know that the number of jobs between setups is going to be 10, so 10 jobs before we perform a setup, and the time for that setup is 2 hours. So from there we can compute our effective time, which is going to be equal to T0 plus the time for setup divided by the number of jobs between setups. And in this case, this is 1 hour plus 2 divided by 10, which equals 1.2 hours. And our effective capacity is going to be 1 over TE. So in that case, that is 1 over 1 plus 2 over 10, which is equal to 0.8333 jobs an hour. Okay, so for this fast, inflexible machine with a 2-hour setup, every 10 jobs, we have an effective capacity of 0.83 jobs an hour. Now, we want to compare this with a slower flexible machine, which will not require any setups. Okay, so we're basically comparing setups against a machine that doesn't require any setups. Again, first machine is going to be fast, the second one is going to be slower. So, in terms of the time, since this one is going to be slower, that effective time, or that time to process that part, is going to be 1.2 hours. And we can compute the effective capacity. Since this one has no setup, we don't have to take into account that variability. So the effective capacity is 1 over T0, which is 1 over 1.2, is 0.833 jobs an hour. Okay, so using the traditional analysis, we notice that there's no difference in terms of the effective capacity. Okay, so even though we are looking at two different types of processes, if we use the traditional analysis, we see that it shows that there's no difference between these two machines. So I'm going to give you some time to write those notes. So on the next slide, what we want to do is we want to compare the mean and the variance for the same example. So we're going to start with the same machine, the fast inflexible machine with the 2-hour setup. So this is given. The time for processing that part is 1 hour. And we also know the coefficient square, which is 0.0625. And this is coming from the variance. So remember that this is the square of the mean divided by the standard deviation. We also know that we have 10 jobs between setups. And the time for setup is 2 hours. So we can also compute the coefficient of variation for that setup 0.0625. Well, that's and now we can compute the effective time for processing. We can compute the capacity or the effective capacity for the process. And we are also going to look at the coefficient of variation by taking into consideration the variance. Yes. This one, these are given. So this is basically the variability of the setup. So this is the time of the setup divided by the variability of the setup squared. But the problem is giving it to you. Square. Yes. This one? So it's CS squared. Oh, yes, the opposite. Correct. Yes. Thank you. Yes. So my bad is the opposite. Thank you. Yes. Okay, so so now we're going to take into account the variability of the process. So we can compute the effective time, which is equal to Z0 plus TS over the number of jobs between setups. And we know that is equal to 1.2 hours. RE, we know, we computed that before on the previous slide. That is equal to 0.8333 jobs an hour. And now we're going to use this expression here to account for the variability of the setup. Okay, so that is going to be equal to sigma of the natural variability plus t time of the setup square times zs square divided by ns plus ns minus 1 divided by ns square. And if you input the parameters, corresponding parameters there, you will get that this is equal to 0.4475. And if you can double check this for me, the C square should be equal to 0.4475 divided by 1.2 square, and that should be 0.31. Okay, so the coefficient of variation square is 0.31 for this process. Now we want to compare this with our slower machine with no setups. Okay, so I'm giving you some time to write your notes. Okay, so on the next slide, we're gonna perform same analysis, but again, this machine has no setups, so we don't have to account for the variability in that sense. We know that the time for processing a part is 1.2 hours. The coefficient, the square coefficient of variation is 4.25. So if we compute the effective capacity is 1 over T0, which we already know is 0.33 jobs an hour, and the square coefficient, effective coefficient of variation, will be equal to the square coefficient of variation of the natural process, which is going to be the same because we have no setups. So as you can see, this value, 0.25, is smaller than the coefficient of the square coefficient, effective coefficient of variation that the machine that is faster with setups. Okay, so in conclusion, based on this analysis, flexibility can reduce variability. So even though this machine is slower, it allows you to have more flexibility in terms of changing products without having to perform a setup. And that reduces the variability. When you compare against a machine that is faster but requires more time for setup. We also have on the next slide a third machine that is the same as the previous machine, same as this one, but now with setups that are shorter and frequent. Okay, so we're going to add some setups to this machine and we're going to see what's going to happen in terms of the variability. Okay, so a new machine, a third machine, same as the previous machine with setups, but with shorter, more frequent setups. So the setups are going to happen every 5 jobs, and the time for setup is 1 hour. Okay, so the effective capacity is going to be 1 over TE. So now we need to account for the setups for this machine. So this is going to be 1 over 1 plus 1 over 5, which is equal to 0.833 jobs an hour. Okay, so same as the other two machines, 0.8333. So the typical analysis doesn't tell us a lot. But now we're going to look at the variability, right? So we look at the effective square. So this is sigma of the natural process square plus the time to setup times CH square divided by the number of jobs between setups plus NS minus 1 divided by NS square. And this is equal to 0.2350. So now by adding these setups, we can see that the variability is actually reduced. So in conclusion, shorter, more frequent setups induce less variability. Actually, we need to compute the coefficient, the effective coefficient of variation as well, and that is 0.16. So as you can see, there's a lot of things that we need to take into account when we are comparing these systems. First, the type of variability that the process is inherited in the process. So if you have a machine with setups, you have a machine with no setups. If you have a preemptive variability that can also affect the process. If you need to add a non-preemptive variability that also will affect the variability of your process, obviously. So, so the analysis will depend on the type of system that you have on your manufacturing process. But as part, I mean, if you think about this in terms of the evaluation that I'm going to make in the exams, you see that there's a lot of equations and it's impossible for you to memorize all of them. So most likely for the exams, you're going to have some type of formula sheet. Okay, so don't worry about memorizing all these equations. The important thing is that you know when to apply them. Okay. So there are other process variability inflators, operator unavailability, recycling, batching, material unavailability, etc., etc., etc. So there's a lot of things that can actually add variability to your process, and the effects that will have is the inflation of your effective time and the coefficient on the effective coefficient of variation for your system. So effective, as a consequence, effective process variability can be L2P1-B or high variability. And you remember the three intervals that we discussed to classify your process between low variability, moderate variability, and high variability. Okay. So on the next slide, I'm going to show you a summary of all the equations that are associated with your process, and depending on the type of variability that you have, these are the equations that you are going to be applying. So if you have natural variability, preemptive variability, and non-preemptive variability, and there are some examples also linked to this type of variabilities and the parameters, and how to get those from the specific system or process that you are analyzing. So having something like this as part of the formula sheet will be beneficial. Okay, so this slide concludes the variability portion. Now we're gonna continue talking about the variability inherited in the machines of the process. Now we're gonna talk about a different type of variability, which is most related to the flow of the entities. So how the arrival process affect the variability of my process. Okay, so that is what we call flow variability. And to illustrate the concept, variability of one station can affect the behavior of other stations. So we are thinking about systems that are in a line in a serial fashion. So you have a machine after the other, not in a parallel way, at least for now. So the variability of one station can affect the behavior of the other stations in a line by means of another type of variability, which we call flow variability. Okay, so the idea here with this table is to show you the difference of what we refer to with low variability and high variability. So even though you can see more dots in this line or more parts in this line, you'll see that they are spread in a, or it's not the same space between them, but it's almost the same. So they're spread nicely in their arrivals. But when we have a high variability, that's not the case. So you're going to have a group of them arriving together, and then there will be some time with no arrivals, and then another group, maybe you get another one by itself, and so on. So now it's not spread as nicely as the first one, so that's what we call having a high variability in your arrival process. Okay, so one's smooth, the other one is bursty. So in order to measure the flow variability, we have these same parameters. Now we're going to use a index A to represent the arrivals. So we have a mean time between arrivals. We have an arrival rate, which is basically 1 over this EA. This one is giving you the time. So a part would arrive every 15 minutes. This one is basically giving you the opposite. I would expect 10 parts per hour. Okay, so one is in terms of time, the other one is in terms of the units. We also have a standard deviation of the time between arrivals, and obviously the coefficient of variation of the inter-arrival times. So in order for the workstations to keep up with the arrivals, the effective capacity must be higher than the arrivals capacity. So you should be able to process a little bit more than the parts that they're arriving in your process. So on the next slide, we have a representation of how this variability is spread throughout the system. So for example, you have station I, and then you have your second station coming after that. So you have a variation or variability coming from the input process here, which is going to be combined with the variability of your process, and that's going to be reflected on the output of that station. What happened is that combination of variability is now the input for the next station. So that variability is going to be moving to the next station, and it's going to be combined by the variability on the next station, and so on. So you're basically, every time that the part goes through the process, you're adding more variability to your processing in the manufacturing line. So in terms of the single machine station, we want to compute this coefficient of, square coefficient of variation of the departures from the machines. And it's basically the combination of these two, which is what we're trying to express with this equation right here. So the departure variability depends on the arrival variability and the process variability, combination of the two. Where U is the station utilization, given by U equals RA times T. If we have a multi-machine station, now we have multiple machines in parallel. We can also perform a similar analysis, which is given here, multiple machine station. So we can compute also that square coefficient of variation for the departures, and obviously you need to count the number of machines that you have in that station now. So the expression changes a little bit. because now you have to take into consideration the variability on the other machines. Okay, so M is the number of identical machines. So we are assuming that all the machines are the same. We have the same machines for the same station. And U is going to be equal to RA times T divided by M in this case. Okay, so now we are looking at the variability and the propagation of the variability in terms of the arrivals to your system. So, for example, if we have the propagation of variability for a high utilization station, meaning that this machine will be occupied most of the time. So, if you have a high utilization station and you have a high variability, even though you have a low variability arrival process, the departure variability will have a high variability. And that's what this figure is trying to illustrate. So the high variability, basically, the station is providing you with the variability of the departure process. Okay? So same thing is going to happen if you have a high variability for the arrival process and your process has a high variability, most likely the departure variability will be high. In the case in which you have a high utilization station, so all these three cases, the station is highly utilized, meaning that your processing time is high, for example. So it will take an hour for completing this every part. So if you have a high utilization station and you have a low variability arrival process, most likely the departure process is going to be also low variability. And same thing here, even though you have high variability in terms of your processing, in the arrival process, if the utilization of the machine is high, but you have low variability, your departure variability will be low variability as well. So for the case in which you have a high utilization station, the departure variability is going to be based on the process variability. Okay? On the next line, so in conclusion, the flow variability out of a high utilization station is determined primarily by the process variability at the station. On the next slide, we have a low utilization station. Okay, so now we have a different type or different level of utilization for the station. And if you have a low variability, with a high variability process, now you see that that's not changing your departure variability because the station is low utilized. Okay, so the variability in the process is not affecting your departure variability. But if you come with a high variability and the process has high variability, then you're going to end up having high variability anyway. Now, if your process has a low variability and you have an arrival process with low variability, the departure will also have a low variability. And in the case in which you have a low variability process, even though you have a low variability process, the arrival process is the one that's going to determine your departure variability. Okay, so for a low utilization process, then the departure variability is going to be based on the type of variability that you have for the arrival process. Okay, so those are the two major differences, or the major difference between the two. Again, we are comparing low utilization and high utilization. For the high utilization, the departure variability is going to be based on the process variability. In the low utilization, it's going to depend on the arrival variability. So in conclusion, flow variability of a low utilization station is determined primarily by the flow variability into that station. So in terms of, again, this is the same slide that I show you. So we can compute the propagation of that variability by using this equation for a single station machine and for a multi-station, the equation at the bottom. Okay, so this basically concludes the first part of this lecture for variability. We're gonna transition to the second part in a minute. But some of the takeaways that you need to understand from this lecture, the variability measures of coefficient of variation of the effective process time and the coefficient of variation of interarrival times, the component of process variabilities, including failures, setups, many others, display capacity and inflate variability, long infrequent disruptions worse than short frequent ones, and consequences of variability. Variability causes congestion, and we're going to look at that on the second part of this lecture. Variability propagates, as you saw on the departure variability, and variability and utilization interact. And we're going to talk about this on the second part of the lecture, full variability, less destructive than individual variability. Okay, so that concludes this first part of the lecture. Let me move to the next group of, and I think I was able to save